All right, hey guys, and welcome back to another AP Physics C video. Today we're going to do the rotational inertia of a non-uniform disk about its center. This is where the disk has a surface mass density of sigma r. I'll just use this laser of sigma r right here, and where b is equal to beta r, where b is a positive constant and r is the radius of the disk. So now let's just jump right into this. We know that the rotational inertia of an object that is not a point mass is equal to the integral of r squared dm. But now we're going to think, why? Why is it that? If we visualize the radius of this disk at some point r, where r is less than, right, this entire, or less equal to 0 or less than r, it's within that range, then we know that it has a little circle. If we visualize as a little hoop like this, let's visualize a little hoop like that. And now I'll maximize that hoop. I'll draw it out. So this is what those little dots I just drew correspond to. Let's move that like that. It's not the perfect circle, but hopefully you get it. Wait, no, I want to move this more. So that's what I just drew, right? If I zoom in here, just this is what I want you guys to see. Let's say at some radius r, there exists a hoop with an infinitely small dr, right? That's the spacing of the hoop, right? So at this r, there exists that little hoop with spacing dr, and the hoop has to have mass dm, because for a little dr, there exists a little dm. But now we need to ask ourselves, what is the area of that little hoop dA, right? Because what I want to think about is if I sum up all of these little hoops, like going from 0 to r, that are infinitely small, shouldn't that give me the entire rotational inertia of that disk? So let's think, if I sum up, if I take these little hoops, because I know the rotational inertia of a hoop is mr squared. So, so if I take that little mass dm of the hoop, and I know that it was at radius r, and I sum all of, oh, I wanna erase this, and I sum all of those hoops up from 0 to r, well, doesn't that look like my rotational inertia equation? Yes, it does. So that's where that comes from, and hopefully you can understand that conceptually. So now I want to also think this little hoop has dA, where all of this is dA. But we know that if I take area as a function of radius, actually I shouldn't do that there. If I take area as a function of radius, which would be pi r squared, and I differentiate that with respect to r, I get 2 pi r, right? And now I multiply dr, I get dA is equal to 2 pi r dr. And that makes sense, doesn't it, right? So now let me put it in a different way. Let me put it in a different manner of speaking. That little hoop, if I cut it right here and I unravel it, guess what that becomes? A rectangle, right? And the rectangle, I said its spacing was dr. But now, well, what would be the length of this rectangle, you might be asking me. I want you to take a guess. And if you said circumference, you're right, because the circumference is 2 pi r. Because if this spacing, you might be saying, well, this radius isn't the same as this radius. Because we have such little small spacing dr, we're allowed to say that those radiuses are the same, where the radius is this little radius I drew over here, r. So now we know that the spacing of this rectangle, and now another thing you might be thinking is, well, that a circle does not equal a rectangle. You can't treat it like that. When we go infinitely small, when we say we go to dr, when we make the spacing dr, we're allowed to treat it like a rectangle. That is how calculus works. And now you might be asking, well, what's the dA? What's the infinitely small area of that little hoop? Guess what? It's length times width. And what does that look like? The same thing up here. So there's two ways to get to that. I personally prefer going about this way because going through the conceptual manner of, well, there's this little spacing dr, and if I turn that into a rectangle and I know that its length is the circumference, no, you don't have to do that. I only showed you guys that because that's the conceptual understanding you need to have. So now that we've gotten through that, we have the conceptual understanding. We can just go through the algebraic methods and the calculus methods of using and deriving dr for dA. So hopefully that makes some more sense because that's the way I learned it, and it's a really useful way to understand it. So now let's keep going. So now I know, well, why am I interested in dA? The reason why I'm interested in dA is because sigma, which is surface mass density, by definition is equal to dm dA. So since I know sigma and it's a function of r, if I multiply this is looking really bad. Let me zoom out. If I multiply sigma by dA, that should give me dm. And now I have known quantities that I can sub into the integral. But first, I'm going to simplify on this side. So I know sigma, they gave it to me. It was br, right? And dA, I just solved for. It's 2 pi r dr. And that is equal to dm. So now I'll sub all of that good stuff into my integral. And I knew that I had to integrate from 0 to r, like I said earlier. You can rewind if you need more help with that. Oh, my mic just, okay. Sorry, I might have just hit my mic and that hurt. Might have sounded really bad. But now let's sub everything in. I'll sub in dm. So br times 2 pi r dr, and now I'll multiply by that r squared that I'm pulling down. Here's where dm goes. And yeah, so now I'll just take out my constants and make this integral look a little bit nicer. So 2 pi and b are constants, and I'm going to have r times r squared dr. Oh, well, what does that get me? That gets me 2 pi b, the integral from 0 to r to the fourth dr. And what does that integral turn into? Well, that will turn into 2 pi b r to the r to the fifth over 5, because that's how integrals work, 0 to big R. And now, by subbing in, using the fundamental theorem of calculus, I'll sub in my endpoints, and this becomes 0. So my final derived rotational inertia is 2 pi b r to the fifth divided by 5. And there's your answer. And hopefully that made sense. And yeah, that's pretty much it. Hopefully this helped. I know it helped me when I first saw that little rectangle thing, because now you know two ways to think about it. So now that you understand the little rectangle, the little taking out little hoops and knowing that the rotational inertia of a hoop is mr squared, you can just sum up all those little hoops and eventually that will give you a disk, right? But yeah, hopefully that helped, and I hope you guys do well on AP Physics C, and I'll see you guys in the next video.